An optimization problem. We have a beautiful open box to put all your maths books in, right? So it needs to be big enough. However, we are restricted by the rectangular piece of cardboard, right? Because I'm on a budget, so you only get a 20 by 30 centimeter piece of cardboard, right? And to make the box, you remove the corner squares, right? So these are all the same length, and then fold it along the dotted line to get that open box shape. Now we want to find the maximum possible volume of this box given our constraints. So first of all, when dealing with any optimization problem, what are the things that you can change? Right? What's your variable? In this case, it depends on x, where x is how deep we make our cuts, right? How big these corners are. So x is all round, because they're all the same length, right? Or if you want a nice neat diagram, we can always use our geometry notation to indicate the same lengths. Beautiful. So we've introduced our parameter. Now we're looking for a volume, so we can express the volume in terms of this variable x. Alright, so let's have a think. So this length here is 20 minus 2x. Right, so that x there and that x there are taken away from the 20, and we're left with 20 minus 2x. Similarly, for the length, we have 30, right, as our maximum, minus 2x again. So we have the dimensions of our box in terms of x. So what would the height of the box be? When you fold it all up, the height would be x. Right, so we have length, 30 minus 2x, width, 20 minus 2x, and height, x. And if we're looking for the volume of the box, we can now express that in terms of x, because we know volume is length times width times height, and each of those terms we've expressed in terms of x. So length 30 minus 2x, width 20 minus 2x, and height x. Great, so we're halfway there, maybe. Yeah, so optimization problems do get a bit long, especially when you're justifying them at the end. However, the key step we just did was to introduce a variable, if it's not already given, and we found an equation relating that variable, the thing we can change, with what we're trying to maximize or minimize, right? In this case, volume. However, we know we're doing calculus, so we're going to want to use that at some point, right? Namely, differentiate it. However, as it stands right now, it's in factorized form, whereas we know how to differentiate a polynomial when it's fully expanded. So let's first expand. So 30 times 20 is, 600. 30 times minus 2x minus 60x. Minus 2x times 20, minus 40x, minus 2x times minus 2x, plus 4x squared, and that's all times x at the end. So expanding that out further with the x becomes 600x minus 100x times x minus 100x squared plus 4x cubed. So we have our relationship with volume and x. So if we're trying to maximize this, let's just think graphically for a second. So if we were to graph our equation for volume, 600x minus 100x squared plus 4x cubed. Now, what's going to be... So what's happening here is my window's not very well situated for this problem. So I'll adjust that a little bit. 0, that looks good. Y min, 0, max. Oh, beautiful. So we can see a cubic, which is kind of obvious because it was 4x cubed, right? However, what's interesting about this now is we can see that there's a maximum and a minimum. Now, for our box, we would like there to be a maximum volume. So G-solve max. So actually, just looking at this, I know the maximum volume is going to be 1056.3 centimeters cubed, just by graphing it. However, we need to show that answer using calculus. So let's do that now. So we have our equation for volume for a maximum. So for max, if your name's Max, congratulations. For maximum, the gradient, right, the derivative must be equal to 0. More generally, that is actually the turning point. It could be a minimum, right? And we'll need to address that afterwards. But so let's work out the derivative of volume with respect to x. So 600x, the derivative is 600, minus 100x squared, the derivative is minus 200x, and the derivative of 4x cubed is 12x squared. Right, so we differentiated our volume equation. And now, like I said, we want there to be a maximum, so we set it equal to 0. So now we have a quadratic equation, and when we solve for x, what that will be telling us, hopefully, is that x equals 3.9 or x equals 12.7, right? Our maximum and our minimum. Cool. So just looking at this, it's a little bit hard to solve by hand. Of course you can. However, at this stage, I would personally use my calculator to solve for it. So to do so, menu, equa. We are using F2, polynomial solver, degree 2. That just means it's x squared is the highest power. And see, we have ax squared plus bx plus c equals 0. So 12x squared minus 200x plus 600 equals 0. I just, exactly the same thing, but I just reordered it, so it's a bit more clear. So n for A goes 12, n for B minus 200, and n for C positive 600. Write the coefficients of each term. We then hit F1, solve, and there we go. We get x equals 12.7 or x equals 3.9. Yeah. And that's absolutely fine to use your calculator there. Alternatively, you could use the quadratic formula, or you could complete the square. Alright, now that we have this x value, what would the volume be? Right, so our next step. So when we need to try both, because we are sure which is the maximum, but assuming we didn't graph it. So when x equals 12.7, the volume would be 600 times 12.7 minus 100, 12.7 squared, plus 4, 12.7 cubed. So all I did there was substitute in 12.7 in for x in our volume equation. And I'm definitely not doing that one in my head. Menu, run maths. There we go. Cooperate. Alright, so just inputting that. So 600, 12.7 minus 100, 12.7 squared, plus 4, 12.7 cubed, minus 315.5 centimeters cubed. Alright, interesting. That's not looking too good. Now when x equals 3.9, we'll see what the volume is. And with movie magic, I already know the answer. Well, we both do because we saw it on the graph. 1056.3 centimeters cubed. Therefore, there is a maximum volume of 1056.3 centimeters cubed when x equals 3.9 centimeters. Awesome. So, on that last note, a reminder for excellence in calculus, you very often need to justify your solution. So how we justified it in this situation is, firstly, we set the derivative equal to 0. So for maximum or minimum, right, in other words, a turning point is when the derivative is 0. We found that at x equals 12.7 or 3.9, we would have a turning point. However, to distinguish which is max or min, we substituted that value back into volume. And when we substituted in 12.7, we got a negative volume. So where does that come from? If we have a think about, if x is negative 12.7, that means instead of going this way, 12.7, it would go inwards 12.7, and since it's going inwards and they overlap, right, we get this interesting like skinny rectangle box thing. So the negative doesn't really make sense because we're cutting paper. However, you could form a box of that shape, right? So which is why we got a negative volume. But when we substituted in 3.9, we got a positive volume, and it was much greater anyway, right? Which indicates that the maximum volume was at 3.9 centimeters. Cool. So just one more time to step through this one. So excellence problem. Firstly, we introduced a variable x, and we expressed the volume in terms of x. We expanded it so we could differentiate it. And in doing that, that is an achieved skill. We acknowledged for a maximum or a minimum, right, for a turning point, we must equate the derivative to 0. Oh, excuse me. The a should be here, right? Once we found the derivative, we set it to 0, and we solved for x. And so, solving for x, we use our calculator, because why not, right? And you could have used the quadratic formula, that's fine too. With those values, we substituted them into the volume equation for both values of x to find the volumes. We then confirmed, right, that the maximum was at 1056 in our concluding statement. So actually working out those volumes is merit, and justifying it is excellence.